want to say just a little bit more about the scalar triple product and the vector triple product. And then the last topic that we're going to take a look at in this section is torque. With the scalar triple product, we proved in the last video that the volume of the parallel pipette we get, determined by 3 vectors in 3 space, at least in the non-degenerate case, we proved that that was going to be the absolute value of the scalar triple product. And it was a fairly involved proof. Yes, you should study that. Yes, I might ask you about it on an exam or a quiz. Now, I don't think there's any value to your memorizing it and being able to regurgitate it. I want you to study it so that you understand where it comes from. So, on an exam or a quiz, I might ask you about just part of it. I might ask you to calculate just the area of the base or just the height. I might ask you for the whole thing, but if so, I would guide you through it. I would say calculate the area of the base. Okay, now calculate the height. Now multiply them together to get the volume. So you can sort of break it up into chunks, and I would give you those chunks to help you through it. So study it so that you're understanding where it comes from. The vector triple product of 3 vectors is defined to be this. I just want to remind you that's not the same as A cross B cross C, because we don't have an associative law. Really, the only thing this textbook uses this for is Kepler's laws. And I've said 2 things about Kepler's laws. One, when we get to that point in the semester, it's going to be an optional topic for those of you who are interested in it. And 2, I'm going to actually present the derivation of Kepler's laws using a different argument than what's used in the book. So we're not going to be using a whole lot of the vector triple product. So don't worry too much about that. Just remember we don't have an associative law. Okay, torque. That's going to be when we have a force that's causing something to rotate. So here's the scenario. Let's suppose I have a bolt here, and I'm going to try to turn that bolt by using a wrench. I'm going to let the R vector represent the wrench. I'd attach the wrench to the bolt here, but then the wrench would extend out here, so I'd have my hand at the end of the wrench, and that's where I'd be applying a force. So I'm applying a force over here to try to affect an object that's over here. Let's just suppose our force looks something like so, and I'm applying this force hoping it's going to cause the bolt to turn. I'm not attempting to move the bolt left or right or up or down. I'm attempting to turn the bolt. All right, the torque is defined. I'm going to just use a capital T with a bar over it to represent torque. The book uses a Greek letter tau. That's a little bit more standard. I'm just really bad at drawing Greek letter taus. So I've decided, after years of embarrassing myself, that I'm much better at drawing capital T's than Greek letter taus, so that's what I will do. And you are free to use T's or taus for your torque vectors. Okay, it's defined to be R crossed with F. Okay. And I want to just take a look at what the magnitude and the direction of that vector are telling us. If I calculate the magnitude of the torque, we've got this property that that's going to be the magnitude of R times the magnitude of F times sine of theta, where theta is the angle between them. Now I'm going to add theta to my picture. You might be tempted to put theta here and make it the acute angle, but that's not theta. This is theta right here. It's an acute angle. Remember, the angle between 2 vectors is defined as the angle that they make when you draw them with their tails together. Right now, the tail of F is at the tip of R. If I were to translate it so that I put F with its tail at the same place as the tail of R, I can see that I'd be getting this acute angle. And so here, I just sort of slid F over, and I'm drawing that angle theta here. Now, if I look at this picture, I can see that I could break F up into a component that's parallel to R and one that's perpendicular to R. What I'm expecting the force to do is to cause this bolt to turn. This component isn't going to be doing anything because the bolt isn't going to be moving left or right, but this upward, as I've drawn it, component, the component that's perpendicular to R, will contribute to that bolt spinning a bit. And if I were to calculate the magnitude of that component, which is contributing to the torque, to this tendency to rotate, I can see that, well, this angle would also be theta because these lines are perpendicular. And so the magnitude of this component would just be the magnitude of F times sine of theta. That's, of course, because sine of theta would be the magnitude of this side divided by the magnitude of F. And I just solved for the magnitude of that sine. So this right here, the magnitude of F sine theta, that's the magnitude of the component of force that's contributing to the torque. So what we have is that the magnitude of the torque is the product of this magnitude and this magnitude. The magnitude of the component of force that's contributing to the rotation, and then what I'm going to call the length of the lever arm. General principle in physics is that if you're using a lever to move something, and a wrench is sort of acting like a lever here, the length of that lever arm contributes to the amount of force that you'll get. A longer lever arm is going to give you more force, and in this case, more torque. So the magnitude of the torque is just the product of that lever arm and the component of the force that's contributing to, in this case, the bolt turning. Now, if I look at the direction of the torque, because the torque is defined to be a vector, it's the cross product of these two things. So let's calculate that. Let's use our right hand rule. So I'm going to move F over to here so that I've drawn them with their tails together. Now it's defined to be R cross F. So I'm going to take my right hand, I'm going to put the fingers pointing in the direction of R, and I'm going to curl them towards F. You'll notice my thumb is pointing straight out. Okay, so R cross F is going to be a vector that's pointing straight out from the board. Now, what way is the bolt going to turn? If I'm applying a force like so, well, if there's an upward component, I'm going to be causing the bolt to turn in this direction. Notice, if we're standing out here, from the perspective you've got watching this video, if we're going around in this direction, that's counterclockwise. Now, in free space, counterclockwise is not well defined, okay? So what you're seeing right now is something that's going like so, that looks counterclockwise from where you're looking, but notice if I turn around, I didn't change the way I'm spinning and now it looks clockwise. So what the direction of the torque vector gives us is it gives us a viewpoint. If this is the torque vector, it's when I'm looking from the tip to the tail of the torque vector that the direction of rotation will be counterclockwise. So it sort of tells us where to stand, and then if we're standing there looking down from the tip towards the tail, then the direction of rotation will be counterclockwise. All right, that is torque.